Just started the recording. Thank you for reminding me. And is there any other question? All right, so if not, then I want to go ahead and download the PDF that I just uploaded before the class. It's under your module 11 on Blackboard. So earlier this morning, we didn't have access to the Blackboard. I don't know if you tried to access Blackboard, but it was down. So I just updated the PowerPoint under module 11. So if you go under 11.1, Introduction to Machine Learning, you see a PowerPoint. Formerly from chapter 6, but in the newer edition, now it's changed to another chapter. So you have to figure out what is in the newer version. Okay, so I'm going to go ahead and share my screen. All right, so let's talk about machine learning and see what machine learning or artificial intelligence, or sometimes called data mining, means. So all the method that we learned so far, including regression, forecasting, all of those actually are data-driven method. Basically, it means that we gather data and try to come up with some kind of understanding of these data, like with some analytical method, we try to get a better understanding of this data. Let me see if I can change it to the other. There you go. So this is a better sharing. Okay, so far all the method that we learned was data driven. It means that the main ingredient is data. Unless you have the data, you cannot start developing analytical methods such as regression, forecasting. Artificial intelligence, machine learning, or data mining are all pretty much data-driven techniques. Some of the artificial intelligence are also logic-based. It means that based on some logic, you define, like there's a series of if-then that defines how the program works. But machine learning, the main idea is that you have given data to your algorithm or method, and your method learns from these data and try to use this information to predict the future event. Now, there are so many examples of that we're going to go over in this class, like a few case studies and so forth. But why it's become so important? I would say I think it's about 95% of the data in the world has been generated within the past few years. And the amount of data that now has been produced and electronically tracked is more than ever. It's unprecedented. And that has combined with the ability to gather and save this data and having very strong computational power at the same time. So the three of them together, being able to generate a lot of data, save these data, and have technologies to process these data has given us the opportunity for data mining or machine learning. It means that now you can gather this data to use this information to make meaningful decision. So every day you notice everything you do and everything you say sometimes is going to affect the behavior of some of the tools that you're working with. For example, if you're in your setting, some of your social media's microphone or videos turned on, then they gather the words and informations that you're talking about, and they give you targeted marketing. It was funny where I was looking for some houses and we're talking about ADU, and we're like making fun of the term ADU because everywhere we went to see houses, they said, oh, there is an ADU in the back, which means like there's an independent unit that is kind of like converting your garage to a house. And then all of a sudden I opened my Instagram to see the news for election, and I saw advertisement on ADUs. So you see everything is kind of being targeted. The data is being gathered with the amount that hasn't ever been in the past. And that also means that not only we use this data for good, things, this data can also be work against you sometimes. It's good to get targeted marketing sometimes. I'm looking for insurance and I get all the insurance advertisement. Maybe it can be helpful. But at the same time, you're giving up a level of privacy. But how these models work, like how they learn from even your accent, right? So they're, when you talk to some of these programs, they get used to your accent. Let's say if you have Siri, Siri learns the way you pronounce terms and learn how next time when you said something with your own accent, it will catch it and understand what you're actually meaning. How this works, we're focused on actually understanding these things, and we start from the bottom. Now, if you're really interested and you got really excited about these, and in the future, maybe in your master's program, you can follow like data science or go to data science boot camps and kind of strengthen your ability to work with data, because it's a field that even though there are so many progress, but there's so many rooms for improvement, and machine has not completely replaced human brain, right? So we still have not achieved to that level, even though we have become very accurate. Like when it comes to self-driving machine, there are adaptive learning techniques. Basically, everything happens, the learning experience improves, and the machine learns better and better. In this case, we say machine, it means the algorithm becomes more accurate, but the level of accuracy is not yet to completely eliminate the human observation. So there are so many rooms for improvement in machine learning. So what are the data? Let's talk about the type of data that we can gather. So we have observational data, where basically it means that we record a lot of value, we observe a process, like for example, traffic could be one of the processes that we observe. Typically, these are processes that change on a daily basis. The behavior is not very deterministic. It means that there's uncertainty and there's variation involved with them. So you observe and gather the value associated with that process. And then what you're trying to do, you either try to predict and classify, or you're trying to define patterns and cluster data. Now, if I ask you, what do you think, I want to ask you this question, and I want you to put that in the chat box of what do you think is the difference between these two terms. And the two terms are clustering and classification. When you think about clustering and classification, these are two different terms, and specifically in machine learning, we use them very distinctively because each of them means separate things. So I want to know what you think is the difference between classification and clustering. You can put it in a chat box and we read it through and see if we can gather from your information an idea about the difference between different machine learning techniques. The question is, what do you think is the difference between clustering and classification? So there's some clustering, group data based on similar characteristic. Classification, defining the type of data. It's close. Another one is classification is based on categorizing. Clustering is based on similarity. Maybe classification is more specific than generally clustering. There are some ideas there, still not quite there yet. Cluster is a collection of information. Classification categorizes information. Not there completely yet. Any other idea? The difference between clustering and classification? Okay, so there's one more. Clustering groups data based on classification. Clustering has similarities. Classification is more defined. Close. Elizabeth, you're close. Okay, let me give you some hint here. So the answer to this question actually defines what supervised learning and what unsupervised learning mean. So consider, let me share my screen here, and then I'm going to share screen, whiteboard. So I'm going to switch for a second here. So suppose that you have some information that is coming through, and it's, let's say, think about your email, in this case, like a Gmail account. So a Gmail account, what happens when the information comes in, when the email comes in, they are categorized in 3 groups. There are inbox, or more than 3 groups. Now let's say we just think about the major 3 groups. So there's inbox, there is junk, and there's social, there's promotion. So there are different categories. So let's say you have, in this case, let's consider inbox and junk. Let's say your data is kind of grouped in different, or placed in different boxes depending on their characteristic. Now, how this algorithm works and how it can become more accurate and how it learns from your behavior. So suppose that the first email comes in, and depending on whether that email contained a certain word, it would be junk or inbox. Let's say if it has CPP as the domain of the sender, maybe it's an email that needs to go to inbox, so cpp.edu. So the domain of the email is important, right? So instead of like writing the cpp.edu, I would write the characteristic on the top as domain, right? So domain of the email is important, whether it is .edu or it is like .hotmail, right? So let's say you have another email that comes in and it's Hotmail. And then you have another email comes in that is Gmail, right? .com. This is hotmail.com and cpp.edu. So you have domain as one of the characteristics. There is some terms, like for example, cheap has been identified, like it has correlation with emails that are junk. So for example, the first one doesn't have the cheap term. This one has it, this one doesn't have it. And then you have, let's say, transfer. So transfer money or something like that. So that might be associated with another characteristic of a junk mail, right? So that can actually grow to many more characteristics here. But at the end of the day, what happens is you'll have an idea. So there are so many characteristics. You have a flag here that say either inbox or junk. So if it's inbox, you put 1, otherwise you put 0. So this one is, for example, not a junk. So this is an inbox. So now you have this set of email. This is what we call a training set. So you had a data set that previously from existing email that you kind of have an idea of what is junk that you would perhaps not click on it, and what is the emails that you click on it and you flag it as inbox. Now, when a new email comes in, depending on the similarity of this email with the previous email, so let's say you have another edu that comes in that doesn't have these terminology and has another term that, you know, it's the character, you look at the characteristic and you look that this one is actually that edu. It's very similar to the very first one, so it must be an inbox, right? So you can predict where a new email goes into, right? Whether it's going to go to my inbox or junk, depending on the similarity that it has with the previous emails that went to my inbox. So this is called classification. Why? Because you have classes predefined. So in classification, you have predefined classes. So in classification, you have predefined classes or groups or categories. You look at the new observation. This is a new observation. You look at the similarity of this new observation to the pre-existing observation. And based on that, you say, okay, this needs to be 1 or 0. So that's the meaning of supervised learning. So we call this supervised. Why? Because you're answering the question of whether this email is junk or not based on the idea that is it close to the pre-existing based on the supervision, based on like the observation that you had before, and then you decide to what group you want to classify it. So we call this supervised because your decision supervised by the previous observation that exists here. So what is the meaning of supervised learning? You have a data set for your training where it gives you the answer. So from that data set, you kind of know whether this certain type of email with this characteristic are going to be flagged junk or inbox. And then based on that, you will decide about a new email that comes in, whether it needs to be classified as kind of inbox email or junk. Now, the difference between classification and clustering, or in general, we call them supervised learning and unsupervised learning, is that in unsupervised learning, or yeah, exactly, solid answer. Whereas clustering is analyzing pattern, right? So what does that mean? So if I look at this data set and I don't have information, so momentarily I'm going to take some of these information out. So if I have this data set, but I don't have flags here, okay, so that means I'm going to take these out. So put these back. If I have this data set and I ask you to group the emails for me based on their similarity, I don't have any supervised flag for these. So in this case, I don't know how many groups of email I have, right? I just know that there's certain emails that look alike. For example, they all have the term cheap, they have transfer, or they have money, or all the other characters. So there could be thousands of variables on the top here. So you can make a huge list of variables that needs to be collected for every single email for you to classify it as junk or let's say inbox in the previous example. However, suppose that you collected these, but you don't have any predefined group. You just want to group them based on their similarities. And then the question is to how many groups you want to divide this. You don't really know. You want to know, sometimes you don't know at the beginning how many groups these data would fall into. Sometimes you have an idea about the number of groups. So to give you an idea here, let's look at this example. Suppose that this is your, in a two-dimensional space, you have kind of different observations like this, and your idea is you want to group these observations. So if I want to group this observation, maybe I say these are more closer to each other distance-wise, and these are closer to each other. So maybe I have two clusters. So the galaxies, or it could be a good example of clustering. So what happens is you have a center and you have a lot of stars around it, and you have another center and bunch of stars around it. But in galaxies, what happens is in each of these groups, the stars are very close to each other relative to the other galaxy. So the distance here is very large relatively. So the distance between the two clusters or groups are very large. However, a distance within each cluster is very small. It means that you're very dense. Things are very close to each other within each cluster. However, are too far apart when it comes to the between the clusters. So the ideal way of grouping observation is so that the things that are similar to each other are very close, and things that are different from each other are really far apart. Like, so observation within a group are similar, but too far apart from each other when it comes to the distance of two clusters from each other. So in this case, you don't have a predefined group. Somebody might also think about grouping like this. Okay, you might say, okay, so I'm going to group those in one group and then put these in one cluster and put these in one cluster. So might not at the beginning have a very clear idea of how many groups you want. That's how biologists started to look into dividing the species in different groups. At the beginning, they didn't know how many they have, right? But they look at the different species and they said, okay, this group of species, they all have 6 legs, and they all have this other characteristic that are similar, so we put them in one group. We call them this type of species. But they didn't know how many species overall, how many type of species we're going to have generally. So they just putting things together based on their similarity. They didn't have anything to look back and say, okay, based on this, at the beginning when they started, they didn't know, you know, how many they're going to have in general. So they started like putting things together based on the observation. So that's the major difference between them. And So what we are trying to understand is methods for both classification, where we have observation and we learn from those observations. We call it supervised learning. And sometimes we don't have those, and trying to detect patterns and relationship in data. So this would be example of the, dividing your inbox, mailbox, in mail that you, or incoming mail, into inbox and junk. And this would be the biologist putting things, finding patterns in a species and animals, and trying to put them based on their similarities and relationship into groups. Now, what are the things that we have to do? Either way, the main ingredient of any machine learning technique is data. So we have a saying that garbage in, garbage out, right? So if you have a low quality data that is not consistent and is not gathered with a good level of care, then your machine learning technique is not going to give you a reasonable result. So what we do, we typically start with sampling data, right? So we collect data, we sample data, we clean the data, we call data preparation, meaning that we remove the NAs, or we predict the NAs, or the missing values are somehow compensated for or eliminated. Then we create a model on top of that, which could be in regression, forecasting, could be clustering or classification that we learn. And then we assess the model, how accurate it is. For example, when we talk about k-mean, not k-mean clustering, a moving average. We had a K, which was the parameter that we had to tune. And then what we did, we basically create a model, did the model assessment for different parameters, and we chose the best parameter for that. We do pretty much the same steps in machine learning. Now, how we go about the data sampling? When we deal with, remember with regression, we said when we have a large volume of data, we have to take samples. We cannot work with everything. The way that we do the sampling, if your data is initially a representative sample, then it's good, to take a random sample of that representative sample and do the analysis. Now, before we proceed, I will have a question for you. What is the definition of a random sample? Can somebody give us some description? What do we call a random sample? No one knows? Everybody has taken statistics, right? That's a prereq. Equal probability of any sample. Okay, so we have slow, okay, a sample that has no specific pattern. Equal probability of any sample taken from a population. Okay, so you say the definition is taken from a population. Any sample is taken from a population, right? So let's say, for example, can I take a sample from this class and look at the average GPA of the students in this class and use it as a random sample of Cal Poly Pomona? And say, I took a random sample from Cal Poly Pomona and I'm trying to estimate the average GPA of Cal Poly Pomona. So Alonso says no, because it's only this class. Exactly. So what should I do? It's biased to engineers. Not only biased to engineers, it's biased to industrial engineers who are enrolled in Cal Poly Pomona. So who would need more representation? So exactly, a random samples, random, okay, so you say ask random students you see around campus. Not quite there yet. So the meaning of random, but you're getting close. So you understand that why we cannot represent the whole university by a sample that I taken from this class. Each sample has an equal probability of being chosen. Not quite true there, but close. You take a lot size and from that lot, you take a sample randomly. Not quite there. So I can say I took a random sample, choose from different parts of the range. Okay, for example, one from top value and other. Not quite there, but it's close. So definition of random sample of data equally, exactly. That's the right answer, Kelsey, thank you. The sample of data equally represent the population you're analyzing. What is the meaning of that? If I want to take a random sample, I cannot go just ask anyone in the university randomly and consider that random, because maybe in that day that I took ask student, that was a day that some of the students didn't walk in that area of the campus that I was asking question. So a random sample, it means that a sample that is inclusive. Inclusivity, have you heard of it? But it also exists in statistics. If you want to have a random sample, your data should be representative of all the groups of your population. So basically, if I want to analyze Cal Poly Pomona GPA based on a random sample, I have to make sure that all the groups that are participating on campus have a representative, equal representation in my sample. I cannot have 80% engineers and 20% from social sciences, and they then claim that I had a random sample. That's not true, because the representation of engineers are much higher. So my data is not fairly, my sample is not fairly representing the whole campus community. So that's the meaning of a random sample. If somebody asks you what is a random sample, it's an inclusive. It means that everybody in the population has a equal opportunity to be represented in that sample. Now let's say you take the sample from the data that is representative, and the second bullet is sample is a representative. And when you make a decision about this representative sample, that you can use your inferences and analysis for the entire population of your data. For example, if I take a sample that is representative of engineer and all the other colleges within campus, then whatever I get from that sample in terms of GPA and standard deviation, like average and standard deviation, I can develop some confidence in interval for the whole campus, because now my data is representative. Now, if I want to develop some hypothesis for just the College of Engineering GPA, then I take a random sample from engineering student, and I have to make sure that engineering from all departments have an equal representation in my sample. It might be counterintuitive because you say random, but at the same time, it's not quite random, because we have to go and make sure that we have equal representation in our sample from different groups that participate in engineering discipline. So randomness, it's more inclusivity, but within that, each group, you take random students and ask them, what's your GPA? And then you record that. And then you have, let's say, 4 or 5 engineering department, you gather from each department 3 students, you ask their GPA, you take the average. That average can give you an idea of the whole population average, and a standard deviation can help you to develop some confidence intervals. So that's the meaning of the random sample. So be careful that it's very important, especially when we go to classification, we want to have a good representation of different categories. If I want to classify inbox and junk mail, if my data set is 80% junk and 20% inbox, is not a fair training set. I want to have equal representation of junk emails and inbox emails in my data set to be able to have a good representation. So I don't know if you guys hearing me getting cut off, or how's my voice quality? Okay, good. Because I'm getting like this message that my internet is unstable. I just turned off some of my Wi-Fi in the house. Okay, so hopefully it doesn't get cut off anymore. But so you got the idea of this random sample and what is representative. It means that you have representation. Now, some question earlier was how large our data set should be. Typically, if you have a larger sample, you have a better representation. But for especially regression, we know that if you have too large of a data set, everything becomes significant, whether it is important or not, whether there is a causation or not. So that's not true about machine learning. In machine learning, the more samples you have in your training set, the more examples of junk mail and inbox you present to your algorithm, the more accurate it gets. And that's not one of the, some of the weaknesses of, let's say, regression doesn't exist here. So especially in data set, you want a data to be at least 800, at least minimum 800 row of data, because a small, because if you don't have a large data set, you typically deal, to be honest, in practical cases, you're dealing with million rows, hundreds of thousands of rows of data for machine learning. 700, 800 is not representative of all the possible emails that you can get, right? So the larger the size of the training set, the more accuracy your model is going to have next time a new email comes to your mailbox in terms of identifying whether it's junk or mailbox. So it says a sample of data must be large enough to contain significant information, yet small enough to be manipulated quickly. So what does that mean? If you have like million rows of data, the challenge would be the computational time. Let's say if you have a self-driving machine and every time it sees an object, it takes like 4 minutes or a minute or even like a few seconds sometimes to analyze and figure out whether it's an object or not, or it's a line within in the middle of the road, is not going to be effective, right? So if you have large data sometimes, and depending on the algorithm you choose, the manipulation or basically deciphering the data might take a longer time, and basically you might not have an efficient algorithm. So it's always, when it comes to machine learning, is always the trade-off between the time and the accuracy. If you want something that is accurate, you have to put a lot of data, but if you give a lot of data, you lose the, you're going to have a longer computational time. So what is the optimum trade-off here? You can use, actually, in the literature, there are so many research that find the optimum in between, like to use optimization. What is the best way to, what is the best number of data that we need to consider here to have a good trade-off, optimum trade-off between computational time and accuracy? So it says data mining algorithms are more effective given more data. So they don't have the disadvantage of regression. The more data you have, the more accurate they become. So what is the, okay, so one of the challenges that exist in machine learning is the size of your, not only the size in terms of the number of rows of data that you have. When I say size of your data set, I talk about the variables or the characteristic that you gather information. For example, I was working on a project, and the project was to basically identify counterfeiting website. So let's say you want to buy a brand product, let's say Oakley, for example. You want to buy sunglasses with certain brand, and then you go and search for it, and there's so many fake Oakleys out there which are stealing the traffic from the original product, and that way the company loses a lot of profit because their traffic is now toward the fake or counterfeiting website. So what I had to do was that we get, like, when we search Oakley, we had a list of, like, say, thousands of websites that would pop up. And then I had to flag these websites and say whether they're counterfeiting, 1, or not counterfeiting, 0. Now, there was some gray area as well. So we had some gray area that we, the website that we are not sure if they're legitimate or they're counterfeiting. So for doing this, we had to collect a lot of characteristics about the website. For example, what country is originated from. We, for example, saw a lot of correlation between websites that are registered in China with counterfeiting products. Then what is the domain of the website? Is it some legitimate website, or it's something that the domain is, the domain of the contact email? For example, if you go to the contact section of the website and say contact us, are they giving a Hotmail Gmail address, or are they giving you a corporate domain for their email? Then you had to look at the multiple numbers and characteristics, who registered, what was their city, and a lot of other information. So we had like about 100, 150 characteristics, and some of them were the words that are embedded in the website. For example, you would capture some of these terms that sales, or cheaper, or the best, cheap, like different combination of words that would be associated with counterfeiting websites, or discount, or things like that. And the question now is how you're going to come up with an effective data set, because when you have too many variables, your computational time is going to grow exponentially. And the complexity of your problem grows, how do you eliminate variables that are not important in this case? To eliminate variables that are not important, there are multiple methods. One of them is dimension reduction, which is principal component analysis. We don't really cover that in the context of this class, but it's a huge topic in the context of machine learning, that how do you eliminate extra variables? For example, in a genomic project, you'll have DNA as like the letters as your characteristic, and sometimes, and strand could be 120 letters, and you cannot really decipher all the possible combination used by considering all the possible variation in the DNA, or otherwise you're going to have millions of characteristics. So what you do dimension reduction. So that's an area that we don't really tap into, but it is an area that it's actively being researched and used by researchers out there. So we do really work on data preparation, which is sometimes we call it cleaning the data, because the data at the beginning, we call it dirty or raw. And it might have we would require some preparation. For example, sometimes when we called our data in the R console, we changed the name, we removed the NAs and things like that. And most of the data set that you worked so far with was the data that was, you know, kind of put together and created for this class. So they're very clean, they have all the information you want. But the reality is, when you gather data from different resources, for example, for your project, you might not necessarily have a clean data. It means that you might have missing information or things that you have to compensate for. So how do I do that? Sometimes you use descriptive statistics and visualization method to find out what are the things that needs to be done with the data. For example, as soon as you read your data, you want to look at the summary of the data in R to look at some descriptive statistics. So what is the average? What is the standard deviation? Because if you see NAs or some weird thing in your summary, it means that your data is missing some values, or there are some NAs in there. I have to go back and revise my data. Or data visualization methods. For example, we learn clustering, and clustering can be used for identifying your outliers. Or maybe you can develop a box plot to find your outliers in the data and drop them before you move on. So summary statistic or descriptive statistic and data visualization are mostly heavily used for data, you know, looking at, get a real, initial feeling about your data and kind of moving forward. Now, what do we do if I had missing data? It depends where you see that missing data. So there are multiple ways. For example, let me open this whiteboard here and we can discuss it. So if I have a missing information here, suppose that you have a 4 variable here and you have different observation and you have some flags for them. So this could be, for example, the name of the patient, their body temperature, their race, their city, and multiple, whether they travel abroad or not, and whether they got COVID or not. So that's a type of, if they got COVID, you put 1, otherwise you put 0, right? So suppose that you have this data set. Now you're trying to use this data set to predict whether, if this new person that has came in and has these characteristics, Mexico, let's say they travel to Mexico, and this is their body temperature, and this is some other measurement and criteria that you have gathered. And you want to predict whether this new person has COVID or not. That's classification, right? So you have some information from the previous patients, and a new patient comes in, and you want to predict whether they actually have COVID or not. Right? Especially when the testing was limited, this was crucial because you didn't want to, based on some criteria, you would determine whether this person is legitimate to get tested or not. And it would be based on, you can make a forecast based on some of these characteristics and say, because this person is going to be predicted as 1, it's better to get tested. Otherwise, if it's 0, then the person is not going to get tested, right? So it can be the same thing for a vaccine, right? So now the vaccine is going to come, and the vaccine is going to be in shortage at the beginning. Not everybody's going to have access to it. And the question is, what is the odds of this person is actually getting COVID, so that based on that, we can determine whether this person is eligible to receive the vaccination in the first round, right? So these are things that have real life application. So if I look at this observation, and let's say you have some of the criteria that are missing. So for example, for some of the patient, you don't have information whether they actually traveled abroad or not, right? So you have a lot of NAs here. It's a survey, people didn't fill it out, so you're having missing values. So if you're missing value, it's repeatedly for one variable, then the way that you can treat it is to either eliminate it completely from your data set or try to predict it using the other variables that you have. So in this case, maybe it's difficult to predict whether the person has traveled abroad based on their body temperature and whether they have cough or not and other things. But so in this case, maybe it's more reasonable to drop this whole variable because they don't have too much information about it. So yes, exactly. So that's a very good question, Ernest, because in the machine learning, it doesn't matter that if your variables are dependent on each other as much as it is important in regression. In regression, we said these variables should not have dependency on each other. But in machine learning, it doesn't matter as much. So some of these variables can be driven based on, it can be there can be dependency among the variables, and it's completely fine. That was a very good question. So in machine learning in general, you have so much flexibility because it's not really based on a statistical method as you learn later. And it's more like a heuristic. Some of them are heuristic. It means that it's kind of like rule of thumb and it works fine and you do it. And sometimes they have some solid statistical and operations research background, like support vector machine is a method of classification that has a very strong support from statistics and machine and optimization. It's called support vector machine. But the one that we learn in this class, it doesn't have strong statistical background. So you can easily have different variables that are independent on each other and no problem with that. So the conclusion here, if you have missing value for one variable for so many of them, then it's not worth to make a prediction for it. You simply eliminate that variable from the pool. However, what if the missing information is not for a column, but it's for a row? If I have a lot of NAs in a row, so there is one patient that came in and we don't really have too much information about that patient. We just know they have traveled to, let's say, Canada, and we don't really have other information about them. So in this case, if you don't have a lot of information, you can simply drop that whole row as well. So it depends on how much of information is missing. If there's only one information, that's fine, you don't need to. But if there's so many information missing for a row or for a column, you drop it. Now, what happens if it's sparse? It means that you don't have that many that are missing. So let's say I have only, for this patient, I only have this one, this observation that is missing, but I have observation for other things that they have done. So this is the only one that is missing. So what do I do? Sometimes you can replace this by an average of the whole column. So look at this whole column average or mean and replace that with the average. So if there are a few that are missing in a column, you can always do that. If it's a lot in a column, you remove it. Same thing in a row. In a row, if you see that a lot of information are missing, then you drop the row. However, if it's one or two, you can always replace it with a column average. Never with a column row, right? Because you cannot really take an average of this row, for example, and it does not make any sense. But if I look at the body temperature and I don't have for this patient, I can replace it with the average without interfering much in my data set. So there are ways that we treat the missing values. There are either analytical, you predict one variable based on the other one. You either drop them based on the extent of the information you have, or approximate them using average by the column average. So that's the three ways that you can deal with the missing values. And we're gonna talk about those. So discard observation with any missing value. Observation, remember, is a row of data. So that a row of data is a observation. Discard any variable. Variable is a column. So you can discard any missing variable. To filling the missing entries with estimated value, for example, putting the average or using predictive analytics to approximate a column. Or you can also use classification or clustering to handle the missing values, like the one that I mentioned. Like you can use regression, or you can use other machine learning to predict the missing values that are in the data set. So depending on how much missing, then you can choose either of these data. Now, how do I deal with the outliers? We define what are the outliers in the data set and deal with them. The answer is it depends on the amount of data that you have available. If you have a million rows of data and you're trying to find an outlier, your best bet would be clustering. We're going to talk about clustering. You're going to watch a video in Excel file on how clustering works. Basically grouping data based on their similarity, like biologists putting species into similar groups. You do the same thing. When you do that, you're going to have one group that is completely different from all the other observation. And that group becomes your outlier for the most part. So another method would be box plot, right? So we learned that summary, statistic, histogram, scatter plots, pivot, and all the other tools, whatever we use so far, you can use for data quality and outliers. But for larger data, we're going to use closer examination, which is box plot or clustering to identify those. Now, let's talk about variable representation, dimension reduction. We talked about the dimension reduction. Now, what is a variable representation? As I mentioned earlier, so for example, when your email comes into your mailbox, you're going to have a lot of a way of representing this email. It could be based on the words that are existing, based on the domain of the email that comes in. And these characteristics basically represent that email. And dimension reduction refers to removing variables. But the way you want to do it is that without losing critical information. You don't want to lose information by dropping the variables. For example, in information theory, there is a method that you can basically project data into a smaller dimension and only choose a few that has the highest variability. So basically, if you have a bunch of variables, the idea is if you have a bunch of variables, look at the variability among them and choose the one that has the highest variability, because those are the one that impacts the final result the most. So that's one idea. But there are other things, there are very advanced methods for that, and that if you pursue data analytics in a higher level, you're going to be familiar with those and being able to implement it. Another thing that you have, sometimes you have a combination of categorical and non-categorical variables. So you have variables that are integer, let's say body temperature, and then you have the last countries that a person has visited, right? So you have categorical, dummy variables, and then you have variables that are basically categorical as ones and zeros, and all of a sudden you have body temperature that is 94, and ones and zeros might seem very insignificant relative or small relative to the body temperature, which is 94. So what do? We scale the data in that situation. So when we go to KNN classification, which is K nearest neighborhood classification, you see that in R, we basically, what we do, or we divide our data set into training and test set, and we make sure that we scale the data, bring everything into the same scope. I'm not comparing or body temperature with dummy variable as ones and zeros, because that variable is going to be not equally represented in my data set. So the way that we do that and tackle that is by scaling the data. So typically would be dividing each observation by maximum minus minimum in each column. So you find for each column what is the maximum, what is the minimum. You divide each observation over that max minus min. So that's one of the ways that you can scale the data. That way everything is brought to the scope of 0 to 1, and then everything has given the same weight. So it's not like body temperature has a higher weight than the countries that somebody has been traveled to, or whether they have cough or not. So all the variables are brought to the same scope. Sometimes also it's better to combine some of the variables as opposed to looking at them separately. Think about a good example would be this voting situation, right? So if I want to predict the presidential election, whether a county is going to be Democratic or Republican, right? So you have a classification. You're predicting 0 and 1s. If it's Democratic, let's say 1, and Republican 0. So what are the variables that you think it would be important in prediction of this? Obviously, population is important. The group that, let's say educated group, a number of people that have post-high school education. But then instead of looking at these two separately, looking at post-high school education number, let's say 200,000 out of 100,000, sorry, 200,000 out of 1,000,000 have post-high school education. So that means about 20%, right? 20% of the population have post-high school education. So 20% is a better representation as opposed to two variables that are considered separately, which is post-school and 200,000 and also 100,000. Why? Because if you look at them separately, you don't have an idea. Okay, so you might say 200,000, it's a lot. It's a lot of people that are educated, but, or it could be, you could say, oh, it's very small. You cannot really say its effect unless you have some reference to compare, right? Unless you say, if I say 200,000 out of 1,000,000 or 200,000 out of 10 million, it makes a huge difference. And if you want to have a more accurate, instead of looking at variables separately, sometimes it's better to consider them combined as ratio, so that you say 20% as opposed to 2 columns. So that's another thing when you want to make a representation of your data set, the way that we look at them, especially for your project, it's a good thing to take into consideration. If I want to predict the extent of COVID patients, as opposed to look at population and separately, maybe I should look into the population density, right? So basically it means that the amount of people per square or per block or per square feet or per square mile, because the more dense the area, the higher odds of people getting COVID. So if I compare New York and LA, maybe we have higher population, but New York got hit more than us. The reason for it was because they were more dense, city. So the ratio sometimes makes more sense for your project. And often I see in the few projects that you did not consider ratio. So be very mindful for your project that ratio is always better than separate numbers when it comes to population and representation of some group within the population. So always use that. So then we talk about a little bit of unsupervised. We mentioned that the goal is basically to identify a relationship and pattern. And typically we can do some judgment. We want to group maybe cities based on their vulnerability to natural disaster, or group categorize city based on their vulnerability to natural fire that happens. So things like that. Why it's important? Because it allows you to develop some sort of characteristic for the groups. So what is in common among these cities that have a tendency to have, let's say, fire? What are the things that we understand from here that we can use to prevent situations like that happen? Or what is in common within groups that have different groups that have acquired COVID? So there is different racial or it could be different ethnic backgrounds that hit by COVID differently. And why is that so? And by studying each group, you can understand some patterns and things that are helpful for your future decision making. So the whole idea behind machine learning and clustering analysis is to be able to segment your observation and classify them to make a decision that is mindful and learns from the past experiences. So you don't want to repeat the mistakes that has happened, or kind of find better way of doing things. Sometimes clustering, as I mentioned, can be used for data preparation, especially for identifying outliers, because as I said, when you do clustering and you find a group that is obviously different from all the other groups, and typically it has only a few observations, and that's where the outliers are, and you can use them for identifying the outlier. So the method of clustering that you're going to learn, which I'm not going to go over, you're going to watch videos for those, are hierarchical clustering and k-mean clustering. I think we start with k-mean. It's a little bit easier to start with. In k-mean clustering, you know how many groups you're going to divide your data into. However, in hierarchical clustering, you don't know how many groups you're going to divide your data into. So clustering, the advantage in here, hierarchical clustering, is that you don't have to know how many groups you want to define your data. You just look at data and look what are the similar observations and group them in different groups. I can look at my class as an analogy and look at the students that have similar strength, like their similar score, similar GPA, similar standing in terms of their seniority, and so forth, and group them based on their similarity. I don't know how many I will find, but I start putting them into different groups based on some of these similarities. However, in k-mean, so the advantage here is that you might not have an idea about the number of groups, and it's a very brilliant method to use to start defining your groups. However, in k-mean, you should know how many Ks or clusters you're going to define or divide your data into. So the disadvantage here is that you have to know K. So if at the outset you don't know what the K is, then you probably switch to hierarchical. But what is the advantage of these two? In hierarchical clustering, the computational method is more rigorous. You have more computational time because you're dealing with all the possible scenarios. So you compare each observation with the range of all the other observation and decide whether to combine it with which one in one group, as opposed to k-mean clustering. You just compare each observation with K cluster and see which one is the closest one. So this one, computation is less time consuming, and this one is more time consuming. This week, you're going to watch k-mean by next Wednesday, and you have a little exercise to do in Excel spreadsheet. The week after, we're going to focus on hierarchical clustering, where you actually put data into clusters without knowing how many groups are going to be formed at the end. So based on, it says both method depends on how two observations are similar. But how we define the similarity of two observations? Let's say we have two patients, and for each patient we gathered information about their body temperature, where they traveled recently, whether they have cough, fever, have they lost their sense of smell, and all the other characteristics. Now, if I want to compare the distance, so let's say this vector is for the first patient, all the information that we just mentioned, the body temperature and so forth. This is for the second patient, body temperature, whether they traveled, and cough, or all the other observations. Now, how do I understand or calculate the difference between these two observations, these two patients? The way that it works is, obviously, first you have to define dummy variables for all the categorical observation. And then we're going to introduce method to scale the data. So not everything is all over the places. So everything is in the same scale from 0 to 1. And then we find a difference between a pair of observation using Euclidean distance or Manhattan distance. So in Euclidean distance, you calculate the difference of each of these. For example, if this body temperature is 90, this one is 94, the difference is 4. That becomes 4 minus 94 minus 90 is 4, and you square that is 16, and you go to the next observation. But obviously, when you scale these observations, everything is between 0 and 1. Now you're looking the difference between two observations, and both of these numbers, all these characteristics in each category is going to be between 0 and 1. So then you calculate the difference between these two, U2 and V2, and all the way to UQ, VQ, and square them. So that becomes your Euclidean distance. So first, define dummy variables. Second, we scale. Third, we calculate the Euclidean distance. However, in the exercises that I give you, I skip the scaling parts, just so we go over the calculation of distances. But in general, we have to do the scaling before we move on to the distance calculation. Now, sometimes your data set is not a combination of categorical or and numerical. So everything is either categorical. So if everything is 0 and 1, then you can use the other method of similarity that we just introduced. Before we go to that one, what is Manhattan distance? Manhattan distance is, instead of calculating the squares and then take the square root, you just look at the absolute value of differences. I don't think we have it in the slides here, but I can show it right here that, for example, if you have two vectors, the way you calculate your distance is going to be v1 minus u1 plus v2 minus u2 plus, and it goes to VQ minus UQ. So that's called Manhattan distance or rectilinear distance. Rectilinear or Manhattan distance. So basically you look at the absolute value of the difference between these observations. So we either use this one or the Euclidean distance for calculation of distance between observations. Now moving back to the PowerPoint. So now let's see, for example, this gives an observation here for each customer. Let's kind of give you an example. Suppose that age, whether they're female or not, income, whether they're married or not, the number of children, the amount of car loan and mortgage that they have, whether they have car loan or whether they have mortgage, is given in a vector like this. Now, if you want to, if you have another vector, the difference between U and V can be the difference between kind of these observation in terms of the Euclidean distance. So if another observation is 60, 0, 60,000, 0, 3, and 0 and 0, then you can calculate those differences and look at the absolute value and consider the rectilinear or the difference that are squared and the square root of all the summation to calculate the rectilinear distance. So sometimes, as I said, everything can be dummy. So everything, if your data set is only ones and zeros and you don't deal with any combination of dummy and numerical value, we have another measure of calculating similarities that is called matching coefficient. Basically, in the matching coefficient, we count how many observations they have the matching result. So let me give you an example here that explain it much easier here. So suppose that you have two observations and they are only ones and zeros. And this one is this. So matching coefficient, it says count how many variables the two observations have similar outcome. For example, both of them are, let me use another color. Both of them are 1 in here. So that's 1, 2, 3. So 3 observations, they are matching, right? They have exactly the same outcome out of how many? 1, 2, 3, 4, 5, and 6. So the matching coefficient would be 50%. However, another argument is that this zeros should not be counted as similarity. Because let's say if these zeros are type of cars, let's say if this is Toyota, and if you have Toyota, you put 1, otherwise 0. And this is Chevy, if you have Chevy, you put 1, otherwise you put 0. So if I say a person doesn't have Chevy, if 2 persons don't have Chevy or don't have Toyota, that doesn't mean that they have the same car, right? So they just don't have Chevy or Toyota, but they could have any other car which completely are different from each other. So one could have an Audi, the other one BMW. So another argument is that the matching coefficient is not accurate because the zeros doesn't really represent similarity between observations. So what they revised is that in calculation of similarity, we're not going to count the zeros, we only count 1. So we only count 1, but also we're not going to include these in our calculation. So it's going to be 1 out of 1, 2, 3, and 4. So the similarity between these two is only 25%. So we call this Jacquard's coefficient. So Jacquard's coefficient says count the number of ones, because if both of them are 1, it means that they have, let's say if this was another car, which was BMW, That means it's a categorical, it's a dummy variable for BMW. If two people have BMW, they're exactly similar because they have BMW in terms of their car ownership. However, if they didn't have Toyota and Chevy, didn't mean that they have the same car, right? So what happens is in matching coefficient, we include zeros, but in Jacquard coefficient, we exclude zeros from our calculation. So in this case, you would say 1, 2, 3 out of 6, but in Jacquard, you eliminate the zeros out of the pool and you say 1 out of 4. So now moving to the slides now, and you understand the definition of matching. Number of variables with matching values for observation U and V. Total number of variables, which was 3 out of 6. Now for the Jacquard's coefficient, we say number of variables with matching non-zero values for observation. So we remove the non-zeros. We only look at the ones, which was 1. And total number of variables was 6 minus the 1 that were matching 0. We had 2 that were matching 0, Toyota and Chevy. So 6 minus 2 is equal to 4 in the bottom of the fraction. And the number of matching that are non-zero was 1. Was BMW, so you have 1 out of 4, which is 25%. So this is the measure of similarity where you only have, where you basically have only 1 and zeros in your data set, and you don't deal with any other variable that has as numerical. If you have even one numerical, then you have to scratch that and use Euclidean or rectilinear or Manhattan distance, and on a scale data. So you want to use that method. So the rest of it is starting talking about hierarchical clustering that you're gonna see later on, and we're gonna go over it later on. I'm gonna stop right here. So for the next week, you go to module 11.2. You have an exercise on k-mean clustering. There are 2 examples there, smaller example, a little bit bigger example. And then there's an exercise that you have to complete after watching these 3 videos. There's the first video, which is very short, and then you'll have 2 videos that actually cover the k-mean clustering. You watch those, and then you complete your exercise before the next class. So it's due 5:30 on next Wednesday. In the meantime, if you have any question, feel free to email me. So if you send me an email, for the most part, I'm responsive, and I'm doing my best to get back to you with questions as much as possible. I try to grade your homework early next, not homework, the quiz that you guys had early next week. So before the next class, I am hoping to have done the grading for your quiz as well. Questions? Can you email the details you mentioned in extra credit in the beginning of the class? Yes, that will be posted via an announcement. Any other question?
So if we had like 400 data, 400 like lines of data, would you say it would be enough for doing machine learning?
Perhaps not, but for the scope of this course, let's say if you did want to get extra credit and apply it, I still give you extra credit. But in real world, it wouldn't be a representative data set. Typically, we want more examples, more samples. You can still establish the model, but it might not, when you test it, it might not be as accurate. Another thing is most of you, if you're looking at your regression, your response variable is what? Your response variable is numeric, right? It's not categorized. So if you want to use machine learning, sometimes you have to do one step, and that is to define some categories for your response variable, as opposed to predicting the cost of, let's say, something. You can say whether it's a high cost or low cost. So you have to do some manipulation in your data to first make sure that you have categories as your response variable, and then apply machine learning techniques on top of that. But to answer your question, which was whether 400 is enough, in practice, no, but for the purpose of your project, it is enough.
Okay, so could we do, for example, like the regression model for that data set and then try doing like a machine learning for that
Definitely.
same data?
Yeah.
Okay.
Yeah. Any other question? Excellent. Okay, so assignment, the only assignment due next week, that is correct. So only 11.2 is the assignment that is due next week. All right. Awesome. All right, so I'll see you next week and have a great rest of the week, everyone. Bye. Thank you.
Professor,
Yeah.
actually, is Monday the async class? Because next Wednesday we have off.
Oh, okay. So then we don't meet next Wednesday. So you just have that, and then I'll post another exercise for Monday. So we meet the following Wednesday.
Okay, I just want to
Okay.
make sure. Okay,
Yeah.
thank you.
So this is due next Wednesday. Next Wednesday, then we don't meet, but then I'm going to post you some homework and some stuff to watch for the following week.
Okay. And then
Okay.
are you going to post the assignment for Monday within the next few days? I take it?
Yeah. So I'll
Okay.
post an announcement both for whatever you need to do until next week. And then next week I'll post an announcement for what you need to do for the following week. But you're going to watch actually 2 methods. I think I already posted 12.2. If you want to go ahead and do the stuff on 12.2, that's fine. I'll put a link. So basically until the next time we meet, you should be able to run both clustering method, which is hierarchical clustering and k-mean. But I'll post them in an announcement so we all are on the same page.
Okay, thank you.
All right. Okay, I'll see you next time, whenever that happens. Have a great rest of the week.